The next subtopic we're looking at is 7.2 nuclear reactions. Before we get into the nuclear reactions though, we need to look at a different unit of measurement that we're going to use here. As you can see there, that unit is the Unified Atomic Mass Unit. The symbol for that is a U, and so that's a unit that we'll be using throughout the rest of this nuclear physics aspect that we're looking at. And to explain that, what a Unified Atomic Mass Unit is, first of all need to identify that masses of nuclei are extremely small. So it's on a scale that we can't really wrap our minds around trying to think about how small it is. So instead we use an alternative or an alternate unit is the Unified Atomic Mass Unit. So the reason why we call it a Unified Atomic Mass Unit is that it's a unit that it's not an SI unit as such. It's one that's a commonly used unit and used across the world. In some cases, it's now known as the Dalton, but we'll stick with Unified Atomic Mass Unit. It's what's in the IB syllabus. Now, it is defined fairly clearly as being 1/12 of the mass of a carbon-12 atom. So, first of all, the reason why it's carbon-12. Carbon-12 is one of the most abundant atoms in organic compounds, and so it's fairly widespread throughout the world. Secondly, the 1/12 aspect. You can see there if we've got carbon-12, this 1/12 aspect basically means that it's approximately equal to the mass of a proton or neutron, or proton and neutron. So if you think about that, carbon-12 has 12 nucleons in it, and so if we divide the mass of one carbon-12 atom by 12, we get approximately the mass of a proton and neutron. So the value of that then is, so one atomic mass unit, if we look at the conversion, it's equal to 1.661 by 10 to the negative 27 kilograms. Now that conversion is in the data booklet. It's not in subtopic 7.2, it's actually in the conversions and constants table. So I'll just highlight that to draw your attention to that aspect. Another quantity that is useful to note here then is to look actually at the mass of a proton and the mass of a neutron. If we just state them in atomic mass units. Again, these are in the data booklet, so you can go and have a look at them there. It has the equivalent value in kilograms, but I just want to state here what it is in atomic mass units. And surprisingly, the masses here are not exactly equal to 1. And also, we don't have one that's greater than 1 and the other that's less than 1. So both of them actually have masses that are slightly greater than one atomic mass unit. Now if you think about it and we go back to that definition, 1/12 of the mass of a carbon-12 atom, that doesn't seem to make sense that carbon-12 would be 12 atomic mass units, but then if we look at the mass of the protons and neutrons separately, it's actually more than 12 atomic mass units. So we get this discrepancy between the two masses, and that's basically what the next section of this subtopic is going to be about, looking at that discrepancy between the mass of the components separately and the mass of the nucleus when all of those components are combined. So we'll deal with that in the next video.